Welcome, everyone, to the second installment in our Land Aware seminar series. My name is Lisa Luna. Together with Corey Fraze, we're organizing this series, and we're really happy to have Andrea Carri today with us. Just as a reminder to everyone, we now have a dedicated seminar series event page on our Land Aware website. We can drop that in the chat, and there you can find recordings from our previous webinars and also see what will be coming up next. So with that said, today's webinar is being recorded. It will be posted on the Landaware YouTube channel, and by participating, we're going to assume that you are all right with that. Okay, then jumping in. So today we have Andrea Carri. He is from ASE, Advanced Slope Engineering, and is a civil and environmental engineer. He can introduce himself in more detail, but he'll be presenting on landslide monitoring at the slope scale from challenges to early warning solutions. We'll plan on about a 45-minute talk, more or less, and then we'll have time for questions. So you can either think about questions, drop them in the chat as we go along. We'll address them at the end, or we can raise hands and have a talk. So, all right, Andrea, I'll hand over to you.
Thank you very much. Welcome to this new webinar. I decided to have this theme. So landslide monitoring at slope scale from challenges, and there are a lot of challenges, let me say, to early warning solution. Just confirm me that you can see my screen.
I don't see it yet, so.
Really? Sorry.
No problem.
What about
Yeah,
now?
looks like it's coming. There we go. Yep. Perfect.
Oh, okay, super. So just to introduce myself, as Liza said, I'm the technical director of Advanced Slope Engineering, which is a company from Italy that was founded as a startup back in 2013. And we were born in order to sell a patent instrument developed by the University of Parma. So it started as a research project. Then we patented this new kind of instrumentation for the monitoring of, it's an automatic inclinometer for the monitoring of geotechnical and structural structures, sorry. And since that time, right now we are in 15 countries with over 13,000 sensors in real time. So we have to manage a lot of sensors. And I'm a civil and environmental engineer. And here you can see also my references. I'm on ResearchGate, LinkedIn, and whatever. When we started, we had this idea of a new kind of monitoring because, Italy has this situation, which is very worrying. Over the, let me say, 95% of our municipalities have some kind of risk that could be from landslide, from floods, avalanches, and so on. Sometimes also some of them coupled. So in Italy, you have to deal with natural hazard. It's in a lot of places, it's impossible to avoid it. So you have to manage it. This is why we started to think about new kind of instrumentation to manage early warning. So which is the main difference between the regional and the slope scale? Well, let me say almost everything is different. Because when you are at your regional scale, your focus is to map an area in order to identify the susceptibility or some hazard, but you have low spatial resolution and only generalized thresholds. While on the slope scale, you want to identify a specific phenomena and you want to deal with it, you want to monitor it, and in order to have also a warning system which should be reliable. And so you have a lot of key challenges. Here I summarize some of them. Uh, and then in the next slides, we will see them in detail. The first issue is the site accessibility, because, if you want to install a system, every kind of system, you have to think about the installation and the logistic, which sometimes is very hard because we deal with landslide, so we have to go up on the mountains sometimes, and if you have to think about how you can transport all the instrumentation you need uh, over the mountains, it's sometimes it's difficult, and you have to carefully plan it in advance in order to stay on the budget. It's very easy to go out of the budget because you don't plan the installation carefully. Um, and here you can see an example. So in this case, we had to install using the helicopter, and you have to think that every single flight with a helicopter has a cost. It's per minutes, and it's a lot, let me say. So you have to think about the logistic, how you can carry everything on site, and also to have an expert, a company which is expert in this kind of installation. Because remember, an excellent sensor installed poorly will provide poor or no results. So installation is very, very, very important. Here you can see we had some fun after the installation in the helicopter. It was after 1 month of flight in the Aosta Valley, so it was the nice conclusion of this hard work we did there. And another task is the limited spatial coverage. Because you have very good sensors on the market, but a lot of them provide localized measurements. So, if you do not plan in advance the correct position of installation, you may miss displacement or deformation, um, because deformation patterns can vary over short distances. And here you have an example. Here we were monitoring the landslide, so we have an inclinometer that is going underground, of course, and here we have our gateway just close to a GPS station. And at a certain point during the winter, you have to imagine that this place was full of snow. At a certain point, we probably had a rockfall. I say probably because no instrument recorded it. And you can see the effect of the rockfall. Our pole was completely hit, and it went down. The gateway is still there attached to the pole, but the pole was hit for sure. And the GPS was just a couple of meters far from our gateway and did not record anything. So this phenomenon was identified only because our information was that the solar panel was not charging our gateway. That's crazy because the solar panel wasn't there. It was somewhere hit by the rockfall over the valley. And we identified this situation only some months after, because this was in February, it was full of snow, it was impossible to go there. And only in October, if I remember good, we were able to go there and find this situation. So, only a couple of meters could miss your phenomenon. And another important task is the resilience and the reliability. And again, here you have some examples. They are only examples. But for example, we had to monitor debris flow. And so we had to design a system that is able to detect multiple events without the maintenance, because you may have a first debris flow followed by another, and in the meanwhile you may are not able to go on site, so the system must recalibrate by itself, so it must be resilient. Again, when you monitor in the Alps, sometimes you can only go on site between June or July and October. So you have to guarantee a system that must work between November and May by itself without any intervention. And it is an early warning system. So it should be resilient and also reliable, of course. Or, for example, if you have to monitor the rockfall, after the first rockfall, you can have other ones on the same trajectory. So you have to design a system that, again, can identify multiple rockfall, multiple events without going on site. These are very hard challenges, but not only the the system, the sensor, and so on, but you have to focus on also on gateway data transmission, because you may have a very uh, good system, but at the end, I don't know if you do not have the data transmission, because you may lose the mobile line or the radio line and so on. You are not able to transfer the data to the cloud, because right now everything is working on the cloud. So at the end, you have no data. It's very important to design the system in order to guarantee the data transmission and to have an internal memory on the gateway. So if you lose that data transmission, at the following one, you will send all the previous data. But you have to focus also on the server. Your server must be reachable 24 hours per day, 7 days per week. Otherwise, if you are not able to reach the cloud server, your monitoring is not working. So each component of this process is critical for an early warning system. And when you plan a monitoring activity at a slope scale, in my opinion, you have to focus on these questions. As I said, I work for a monitoring company. So if you come to me and you ask me to design a monitoring system, I will ask you these questions. Because you have very different technologies, and they works they work with their own sensors. So it's very different if you want analogic sensor, a digital one, or fiber optic, because the gateway will be different, and also the cost. So you have to think also if you want cabled sensor or Wi-Fi sensor. Uh, and then if you want to monitor the site static or dynamic. And how many readings do I need to ensure a proper monitoring? Because if I know how many readings I need, I can calculate the power consumption. And after that, I have to calculate the battery and the solar panel if I do not have the electricity on site. And the cost could vary a lot. And again, how can I transfer the data? These are the key questions when you are planning a new monitoring system. Because at the end, you always have to deal with the budget. Um, I personally divide the monitoring activity in three categories. Uh, this definition is from me, but just to give you an idea, we can have a basic monitoring system, an advanced one, and an ultimate monitoring system. And we will see also some case study for all of them. Just to summarize, the basic monitoring system is a monitoring system for data collection for knowledge purposes. It's not an early warning system. It's not an alert system. Uh, of course, you can put thresholds. You can also put some forecasting models, so you are able, if you want, to alert authorities. But it's not an early warning system because when you monitor for knowledge, you do not have the features that an early warning system should have. Because, for example, you can have a single technology from a single supplier. It's okay, but it's okay, in my opinion, only if you want to collect data for knowledge, not for an early warning. We will see it. And so you can monitor only the parameter of interest, like, I don't know, deformation or the water level. And in this case, you may manage the data using Excel. Of course, in my opinion, it's always better to use a data management platform which is automated because nowadays you have a lot of data and it's almost impossible to manage them using Excel. But if you have a single instrument with only a few sensors, you may use this kind of data management with manual with a software. And maintenance, when you have a basic system, is performed only when necessary. Maybe. In Italy, I have to say maybe, because I don't know. Maybe you need maintenance. The system is not working since last summer, and at a certain point, someone will go on site. But if you want to collect data for knowledge, you do not have to run on site instantly if, for example, your gateway is not working. So at the end, this is the cheaper possibility for monitoring at slope scale. But it's important, you have always to plan the budget as per year. The budget is not only for the installation and for the instrument, but it's a budget per year, which is very cheap. The management costs are poor, let me say less than 1,000 euros, if you want an idea. Then we go to level two. For me, the level two is an alarm system, which is the difference between an alarm and an early warning system. Because when you have an alarm system, you identify the event when it's happening. So it's not a predictive system. It just identifies the event when a threshold is exceeded, or for example, a debris flow is passing through your section. And in this case, you have to monitor multi-parameter data, and you must have an automated data management procedure with a software. It could be on the cloud or local, but it should be, must be automated. And in this case, you have to plan a regular maintenance. So I don't know, every year, every 6 months. And sometimes you have, if there's something that is not working on site, you have also to plan a scheduled maintenance when you have malfunction and before severe weather. For example, if you are monitoring a debris flow that is triggered by rainfall, if you are if right now the gateway is not working and and we are in the dry season, you may wait sometimes before going on site. It's always better to go instantly, but you can wait uh, some days or some weeks. But if the weather forecasting says that you will have a lot of rain, you must go on site instantly. So you perform maintenance when before severe weather, for example. All these cases are from real case study from Italy and Europe. Uh, then we have the level 3, which is the most expensive one, and it's per year cost, of course. In this case, it's our predictive system. So, in my opinion, but also not in my opinion, in literature, you must use different technologies. You must have a multi-parameter system, and possible, you must have different suppliers, so different technology from different suppliers. And data management is performed on the cloud. And you have to integrate also numerical and statistical models together with predictive analysis and all these kind of tools. You want to avoid false positives, false alarms, and so on. So you must have a sort of data filtering, AI, and so on, in order to reduce these alert warnings. And my suggestion for maintenance is that I'm talking about Italy, but I think it could be extended. You must have a service contract with a specialized company. Uh, I think that in Italy, the public authorities are not capable, are not organized to go on site and perform maintenance in a very short time. So the best solution is to have a contract with a company, and then you can pretend to have the company solve everything in hours or maybe one day, 2 days, and it works. It works. Of course, it is expensive. So when you plan your budget, you have to think about it. And here I have an example because maintenance is underestimated. I don't know why, but nobody thinks about it. So sometimes you run out of budget before, after the installation, just after the installation. And here you have an example. We are in Italy. This is a town with just over a landslide. All the houses you can see are on over a landslide, which is just crossing the town. We installed 12 sensors, uh, tilt meters, crack meters, inclinometers, and all this kind of stuff. But after some years, only 2 of 12 are working. But it's not an issue of the sensor, it's an issue of the gateway, because here everything was wireless. So at a certain point, you run out of batteries. And you have to plan a very easy maintenance activity. You can perform it in 3, 4 hours in order to change all the batteries and have your system working. And I estimated that the cost, let me say, it's not per year, but the cost for having new batteries and having someone who is going on site to change them is the 3% of the entire amount of the project. But right now, uh, this budget was not planned, so this system is not working. We have only two sensors. It's not working. And if I here I put some guidelines uh, from an Italian public authorities. You have also the link. They are in Italian, but here I translated them into English. And these are the guidelines for the landslide monitoring, and they also talk about early warning procedures and the early warning system. So the definition is that an early warning system should have three characteristics that should work all together. You must have data acquisition continuous and data transmission in real time or near real time. We will see a case study about this. And then you have to plan the maintenance before, so preventive and corrective maintenance. If you do not have one of the characteristics mentioned in this document, the early warning system is not working. And then I talked about data management. So right now, you usually have a lot of automatic sensors. They work very good. They could be contact sensor, remote sensor, photogrammetry, and so on. So you have to imagine that you have to manage a wide range of different data sets, but also a wide range of different gateways and data format. For example, the CSV or the TXT file that's coming from different gateway are different. So you must plan a correct cloud-based platform that is able to integrate everything, but not only sensor and gateway, but also numerical and statistical models, predictive analysis, and also other tools like DTM, GIS, BIM, shapefiles, and so on. And it's very, very complex to have it, but it's the only way you can manage a site properly. And now we go deep into alert and alarm procedures. So after we have installed our system, we have data, and with this data, we are capable to alert uh, the authorities. And we have different possibilities. So we can have multi-level thresholds. This is the easier one. You have a value. If is exceeded, you send an email, an SMS, you trigger a camera, and so on. You can have trigger events, uh, or, and here you have an example of a proper data management system. You can manage a combination of different thresholds. And finally, another important tool is the inverse of velocity method. So let's see some case study. The first one is a combination of different thresholds, starting from trigger events. We are in the northeast of Italy, and here you can have a potential debris flow that could hit an highway. if you look at the image on the left, you can see a road. That road is an highway, so it's a very important one. And you can have a debris flow that is evolving like that, running directly into the highway. And the difficulty is that the area where the debris flow is triggered is just 200 meters far from the highway. So it's very complex to manage this situation. And coming back to my definition, this is an alarm system. It's not an early warning one. It's an alarm system. You identify the phenomenon when it's happening, and we had we had to design a proper monitoring system. So we decided together with our customer to install this kind of sensor. First of all, a couple of trigger. Uh, this is a very easy device, but it works very good. It's just a rope that is crossing a section. And when the tensile force exceed a certain value, it triggers a reading of all the system and a data transmission. So you know in real time that the rope was triggered, and you have also reading from all the devices on site. And we put one in above in the area where the debris flow could start, and one in a section which is in the middle. So the debris flow could cross that section. Then we have a rain gauge, a weather station, because well, we can this site is also managed on rainfall thresholds, and because it's an alert system, you can't predict warnings, but you have weather forecasting, so it's also a way to have alerts based on weather forecasting, and then to verify that alerts with the weather station on site. Then we have a couple of tilt meters placed on some rocks that are potentially unstable. And this is very important, some wire extensometer. They are like the trigger ones, but in this case, we are able to measure the length of the cable. So you can also identify the, the amount of deformation on the cable. And finally, we have a couple of camera placed in these two sections. You can see in this image, you have different ropes at different heights. At the ground level, you have the trigger, and then at 20 centimeters, 40 centimeters, and 60 centimeters, you have the wire extensometer. In order to identify the height of the debris flow, and starting from that information, you are able to know if it could reach the highway or not. And when there's a phenomenon, you can also trigger a photo. So we have two activation. First one was on the 16th of August 2021, where the trigger upstream was activated. So first information is possible alert, but we have also other sensor. And as you can see, the wire extensometer just above the trigger was it. It was deformed by just 2.7 millimeters. So we are not talking about big debris flow. It's just a little phenomenon, but it was it. So you know that the debris flow level reached 20 centimeters, which means level 1 alert. But you also have the rain gauge, and here on site, you have this kind of alert levels. And as you can see, the, the hourly rainfall alarm was triggered. So we have multiple parameters coming all together in a single direction, and the software is able to identify it. Uh, but downstream trigger was not activated. And in the downstream wire extensometer, we had some deformation, but we had the same amount of deformation also the day before. This is very strange because before that, the data were very stable. The day before, we had this kind of deformation that are higher than the one recorded by the wire above. And it's an example of uncertainties of monitoring system. It could be wind, other factors. We have no idea, but at the end, we also have a camera. And it's not so easy to identify the phenomenon, but here you can see that there's something. Nothing really worrying, but there's something. And also, this is the camera from upstream. Downstream, we do not have a photo in real time because the trigger was not activated, but we have a photo the day before and a photo the day after. And you can see that something happened. Nothing worried, but something happened. So if you summarize all this kind of information, the software sent out an alert. Level 1 alert. Rainfall plus trigger plus wire extensometer. And by evaluating all this kind of information, it was pretty clear that maybe the debris flow couldn't reach the highway. So if I remember good, they just closed the emergency lane. But here we have another case study from the same site. It was triggered on the 2nd of November 2023 with the trigger downstream this time, so close to the highway. And in this case, all the wires were triggered with huge deformation. The one at the top was located by 1.4, 1.35 meters. So it's something different from the previous time. And also, if we look at the rainfall, okay, we do not have an alert in the hour before, but as you can see, I remember you that the trigger was at 8 p.m. Between 6 and 7, we recorded 23 millimeters. The alert is at 25, so very close. But between 5 and 6 p.m., so between 3 and 2 hours before the event, we had an alert on rainfall. So we were focused on this side. And we also have an alert for the 24 hours rainfall because we recorded 103 millimeters and the alert was at 90 millimeters. So again, we have a trigger, 3 ropes, and rainfall alert. So this is an alarm, and it's an alarm of level 3, which is the highest one for this site. But trigger upstream was not activated, so the debris flow originates somewhere in the middle. And at the end, we issued the alarm. The highway was closed. And again, uncertainties. We have a camera there, so we were able to record the phenomenon. No, this is the photo. That night, the infrared, I don't know why, did not work. So here we have a clear image of the debris flow. And the only information we had from the site is a photo from above, just 1 hour before the event. We can only see that there's some rain, some wind, but we are not able to see the debris flow at the end. But anyway, this is an example of uncertainties you have to manage during your monitoring activity. But you have all the sensors that are going in the same direction. So level 3 alerts, highway closed. And here we have an image from the trigger that was activated the day before and the day after. And can you spot the difference? In my opinion, no. But when our customer the day after went on site, he found that a debris flow was triggered. So the system was able to close the highway by itself. But it's based on multi-parametric approach. Otherwise, it's impossible. Then, what about inverse of velocity method? So predictive analysis. Uh, we have also this kind um, of predictive tool. So I go briefly into the creep theory. You can have landslide that is prone to fail if you reach the tertiary creep, which means that your displacement are always increasing the displacement ratio. The landslide is accelerating, and if you have a look at the representation with deformation and time, you will reach a sort of vertical line, which means failure. We designed the inverse of velocity method was published in literature in the 80s. We had to design a way to put it in the software as an algorithm. Because in literature, every case study was manually managed. But if you have a lot of sensors around, we have more than 13,000 sensors, you must uh, plan something with a software. And the software could recognize it in real time. So together with my colleagues, we at university, and we published some papers you can find above the references. Uh, we designed an algorithm in order to identify the acceleration phase, because this method works only for tertiary creep. So you have to identify the tertiary creep, not easy. And our first algorithm was based on a geometry. So we try to identify if we have a parabola that is increasing uh, on our displacement versus time analysis. And here you have an example of the algorithm. But at the end, you start from displacement. You calculate the displacement rate. After that, you calculate the inverse of velocity, and you can estimate the time of failure. But again, these work only if you are on the tertiary creep. So first algorithm is able to identify the tertiary creep. Then the second algorithm will run the inverse of velocity method in order to identify the potential time of failure. And here I have a couple of case studies. First one is in the south of Italy, in an area where in the past some landslide occurred, as you can see in the image on the left. And this site was not an early warning one, but just a data collection one in order to build a new road. So data transmission was not in real time. But at the end, at a certain point, we identified with the algorithm two potential landslides. The first one around the 8th, 9th of March, and the second one just a couple of days after. And the system was able to, was activated 16 times, and two of this activation were classified as alarms. So we triggered this alarm. And at the end, this is the situation on site. And as you can see, there are also a lot of manual inclinometer, but Of course, they do not record anything, so you must have automated system if you want to perform early warning, but also if you want to collect data for knowledge purpose, in my opinion. And here you have an example of the warning time. So for the first event, we were able to send the alert 10 hours in advance, but 10 hours in advance because data transmission was not in real time. Otherwise, we were able to trigger it 19 hours in advance. While for the second one, we triggered 3 hours before, but again, if data transmission was in real time, we were able to issue the alert 8 hours before. And the forecasting error for the time of failure is like 1 hour, 3 hours. So the system worked very, very good, as you can see. But this model had a potential bug. And so we developed it in order to avoid false alarms because this model did not take into account the amount of displacement, but only the geometry. This means that if you have a deformation of 1 meter or of 0.1 millimeters, for the model is the same. So we observed that sometimes we had some activation of inverse of velocity method related only to very, very, very little displacement. And we had to plan a way to identify this false positive. And for this reason, a colleague of mine working at University of Parma, Alessandro Valletta, proposed the equivalent displacement threshold theory. So you start from first algorithm that want to identify if you are on the tertiary grid. Second algorithm is able to calculate the inverse of velocity method. And at the end, you have a third algorithm that wants to compare the displacement. So you have the acceleration started yesterday. You compare the displacement occurred in the last 24 hours with displacement of the same amount of time occurred in the past. At the end, you are calibrating the system with itself. It's a threshold that can continuously vary. And you are just saying, right now, I have a displacement triggered by inverse of velocity meter and so on, which is higher than every displacement recorded by that sensor in that site during all my monitoring. This is called the equivalent displacement thresholds. And again, it's in literature. And here we can see an example. We are in a site where we had no thresholds, but we had to guarantee the safety of the workers that has to build this retaining wall. So, you have to guarantee the safety without any thresholds. We use two kind of process. One is the inverse of velocity method. The other one is the state of activity. I will show you. In this site, we had automatic clinometer, we had load cell, and we had strain gauge on the wall. So let's start from state of activity. Our software is designed to identify if a sensor is accelerating, is changing its displacement rate or load rate, and so on. And for this site, it worked very good. We have a first period of time. Here, in this representation, you have altogether some deformation from the kilometers. some load recorded by the load cells, and finally the deformation, the micro deformation recorded by the strain gauge. And as you can see, starting from 2 months before the event, we had the first period of yellow activity. Nothing worrying, but the inclinometer is starting to record something. Starting from 1 month before the event, also the load cell start to record something. Sorry, the strain gauge. And finally, at the end, also the load cell recorded a variation of its trend. And 3 days before the event, we issue an alert only based on state of activity. We do not have any thresholds. But as you can see, every sensor is changing its rate over time. So the software is able to identify it using statistics. And we issue an alert. But we also have the inverse of velocity method that was triggered, as you can see in this image. And below, you can find an example of the equivalent displacement thresholds. And the thresholds calibrated for that time, for that sensor, was 1.5 millimeters. And this event has an equivalent displacement of 2.5. So it's almost the double. We send the alert to our customer. So, and the alert was issued uh, 3 days before. And here you have a camera, a safety camera placed on site that recorded this. As you can see, no one is on site thanks to this alert. And this is a perfect example how you can combine together different methods and technologies in order to have early warning. So, in conclusions, when you deal with slope scale monitoring, you must have a systemic design approach. And then everything should work from the sensor to the gateway, but also data transmission and the server, which should be on the cloud. And you are able to identify the tertiary creep. Of course, it's always possible to improve the method. It's a critical scientific challenge. And in the software, you should have also automatic filtering in order to have a validation of the instrumental data performed by the software. At the end, you have a site that is evolving. So you must have a dynamic approach. You can change your approach to monitoring site during the monitoring activity. And future research should focus also on AI, because right now we are starting to have very useful tools for predictive analysis. And, well, occasionally, it is useful also to have a little help from above. So thank you for your kind attention. This was my presentation.